All right, a lot of what we've mentioned so far about logic is that it's reasoning, and it's reasoning correctly. That's what we're mainly concerned about. But why? Well, we want to take what's correct and then apply that to any new circumstance, right? New situations. And then we want to deduce all possible things that we could know as long as they're 100% correct, right? Deduction, 100% absolute with 100% certainty. In order to do that, we have to recognize what is going on with logic and how it interplays with things that we know. So you have the question of what can you know? What are all these things you can know? What can you learn? What is knowledge? Well, it starts with noticing something, whether that's seeing it or hearing it. You notice it and then you re-notice it. To cognize, right? To recognize is to re-notice. Cognizance is noticing. And then you see a pattern there. Now, all those patterns then you can apply to other things. And this noticing and re-noticing, recognizing, recognizing, all this is just associative learning. So this is all associative. So then you have to communicate. So let's say you have person here, some idea here. We'll just say x squared or something. Okay, so some symbol to represent what he's thinking. There's another person he's trying to communicate it to. Now he has to speak it, right, through a medium, a language, and the other person has to hear it, and hopefully they get the same idea of x squared. Maybe they do recognize it the same way, maybe they don't. So to know all of that, well, we have to apply all the same solid fundamental understanding concepts, deduction, and then applying that pattern onward. So it has to be formulated in a particular way. And language is really important for this. So what is the language? So if you think about this as a tree, so you have some tree that represents everything that you could know. The roots of this tree are going to be your ideas, right? Some kind of ideas, feelings, things that are just there and you notice it in some way. And you get this knowledge, you have this idea. Then you have language, which is your way of describing these ideas. Language is like this trunk, this section, the solid chunk of the tree where you're trying to describe. So in order to then go to these further branches, this language needs to be as rigorous as possible. So the most rigorous, the strongest formalized language we have is logic. This is why computers are based on logic. They're not based on English. They're not based on anything where there might be exceptions or muddy gray areas. It's based on absolutes. It's electricity flowing. Either it is or it isn't. So there's no exceptions in logic. You don't have those exceptions. If there are exceptions or contradictions, you throw them out. And then that's also the rule of math. Math is based on logic. Sometimes you'll get, statistics, let's say, another branch of math where it is based on probabilities and generalizations. But usually, it's not as strong as an algebra that's, straightforward. It's structural. It's completely deductive, absolute and certain. So logic is the most rigorous, and then math, you've got that. Now, really quick as a side tangent here, there is a technique in math called mathematical induction. It is different than induction. It's different than regular induction. Mathematical induction requires you to start with some base case idea, and you prove it and then extend from there to other things, right? Other things that fall into that exact same pattern mathematically. So let's say we have A, and I prove that that is true. Then I'm going to try to generalize that A plus 1 is true. And then I want to take A plus 1 and then plus another 1, right, and show that that is true. So I need to prove it for A, and then A plus 1, and then a plus 2, and I want to continue that on. So this would be an infinite amount of calculation, right? But I don't have to do it because I only need to do it once or twice and then show that inductively it's going to continue that same pattern forever. And I don't have to do this infinite calculation. I can just use deduction, prove it absolutely, and show that it's always going to fall into that same pattern. This is ones and zeros. It's binary. It's trues, falses. That same idea is logic, right? This is logical, mathematical induction, not just a regular induction. So mathematical induction is very different from just like a general induction probability base. So mathematical induction, again, that's for proving things. This is proof, and it's a method. This is a method that is used. Mathematical induction, different than just your regular induction. All right, so going back to this tree idea, you've got your language that describes all these ideas, and it can be done rigorously in logic, and then in math and algebra, and then anything else, whether it's German, French, Spanish, all those languages, they have their own rules. Logic is the most rigorous. It has the most solid structure. It's fundamental. It's absolute. It's certain. But that is only most rigorous if you're excluding induction. So you have to exclude induction. If you don't exclude it, logic becomes the same thing as any other language, whether it's Spanish, French, whatever it might be, English, where there are exceptions, right? It loses its rigor. Computers are, they're using code like C++ or C#. These codes are just languages that are based on logic. They're based on ones and zeros. So logic is the most rigorous. It's this most calculable, most absolute certain way of conveying ideas. So that's why logic is really important, and it's kind of your fundamental case for everything that you're going to do from here on out.